end. I mean, it's not just some philosophical parlor trick, right? It's probably the most profound, most dramatic question any physicist or cosmologist can seriously ask.
It really is.
When you look up the night sky, you see this sense of permanence, stability, history, beauty. But the universe we're in is actually hurtling toward, toward an unknown destination.
The ultimate final act.
Exactly. Is it going to be a slow, quiet fade into cosmic ice?
Yeah.
Or will it be something violent, a dramatic tearing apart of space and time itself?
It is the ultimate countdown, isn't it? The final act of a 13.8 billion year drama. And what's so fascinating, and what we really found digging through these sources, is that the answer isn't in the stars or the galaxies or anything we can see.
No.
The destiny of everything everything that exists, it lies almost entirely in the forces we can't see.
The invisible components.
They're the ones dictating destiny on a cosmic scale.
And that is our mission for this deep dive. We are tackling the really profound topic of the final scenarios for the universe's destiny. We've gathered a stack of cutting-edge cosmological sources. I mean, research into the fundamental composition, the dynamics of the cosmos, and we're going to try to decode the consensus.
If there is one.
Right. We need to understand what the current best science, specifically this thing called the lambda CDM model, tells us about how the lights eventually go out. And crucially, where that model is starting to, to break.
Our guiding tool for this whole discussion is that model, the standard model of cosmology, the lambda CDM model. And that framework, our best guess right now, suggests the universe is heading toward eternal and accelerating expansion.
But as you just hinted, there are cracks appearing in this model, a pretty serious conflict called the Hubble tension.
It's a big one. And that tension is more than just a measurement error. It's really an invitation to explore these truly dramatic alternative end-of-time scenarios. Because if Anna's CDM model is wrong about the expansion rate now, it might be fundamentally wrong about our ultimate fate.
Okay, so let's unpack the composition first. Before we can even begin to talk about the end, we absolutely have to appreciate what it is we're actually analyzing. The cosmic scale is staggering, but the scale of our ignorance is maybe even more profound.
That's a great way to put it. So the standard lambda CDM model, that stands for lambda cold dark matter, it's built on a premise. It assumes that the universe is, on the largest scales, flat.
Flat, meaning like the rules of high school geometry apply. Parallel lines never meet, that sort of thing.
Exactly, Euclidean geometry. And this model, this framework, dictates the percentages of the three main components that make up the total mass energy density of everything. And prepare yourself for that reality check you mentioned.
Right. So if you imagine the entire universe as a giant cosmic pie chart, the sliver representing everything we've ever studied, everything we've ever seen, the stars, the planets, the gas, the dust, it's negligible.
It's tiny.
So let's start with the stuff we do understand, or at least the stuff we can see. Ordinary or baryonic matter.
Baryonic matter is just the stuff made of protons and neutrons. It's what you and I are made of, what the Earth is made of, all the visible matter that classical astronomy has studied for centuries. It only accounts for about 5% of the total density of the universe.
5%. Just let that sink in for a minute.
Okay.
That means 95% of reality is something completely different. It's like being handed a map of a massive new continent, and 95% of it is just shaded black with a label that says, "Unknown territory, proceed with caution."
That's a perfect analogy. That's exactly the predicament we're in.
So what makes up the next big slice of that pie?
That would be the gravitational scaffolding of the universe. Cold dark matter, or CDM. This accounts for a much bigger chunk, somewhere around 26% to 27% of the total mass energy density.
And we call it dark for a very literal reason.
Precisely because it ignores the electromagnetic spectrum. It doesn't glow, it doesn't reflect light, it doesn't absorb light. It's truly completely invisible to all of our telescopes.
But we know it's there. We don't see it directly, but we absolutely know it's there because of its gravitational fingerprint, right?
Absolutely. When we measure how fast galaxies are spinning, they're rotating so quickly that the gravity from the visible matter, that 5%, shouldn't be enough to hold them together. They should just fly apart.
So there has to be something else there, providing extra gravity.
A tremendous amount of extra gravity.
Yeah.
We also see its effects in something called gravitational lensing, where light from a distant object is bent as it passes by a massive galaxy cluster. The amount of bending tells us there's far more mass there than we can see.
And that's the 27%. That dark matter is the necessary gravitational glue. What about the cold part of cold dark matter? Why is that important?
The cold aspect is vital. It means this matter moves non-relativistically. Basically, it moves slowly compared to the speed of light.
Okay.
And the slow movement was crucial in the early universe because it allowed the matter to start clumping together very early on. It formed these gravitational potential wells, little pockets of gravity.
Which then acted like seeds for normal matter.
Exactly. Ordinary matter was then able to fall into these pre-existing wells and start forming the large-scale structures we see today. Galaxies, clusters of galaxies. Dark matter provides the framework. It's the silent architect.
It's incredible. So it ensures that our galaxies don't just fly apart.
Yeah.
But even with that, the dominance of dark matter over visible matter, it's still dwarfed by the ultimate king of cosmic composition.
That is dark energy, represented by the Greek letter lambda. This component is the overwhelming majority. It makes up approximately 68% to 71% of the total mass energy of the universe.
So this is the lambda in lambda CDM.
This is the lambda.
And the discovery of dark energy. I mean, this was back in the late 1990s from looking at distant supernovae. It was a completely revolutionary moment, a total shock to the system, because it proved that the universe wasn't just expanding. The expansion was accelerating.
Yes, it was doing the exact opposite of what everyone expected.
It goes completely against everything gravity, as we traditionally understand it, should be doing. Gravity pulls things together.
Correct. Dark energy is fundamentally different from matter, whether it's visible or dark. The sources we looked at explain dark energy as a uniform energy density that's inherent to the vacuum of space itself.
So it's a property of empty space.
Yes. And its key characteristic, the thing that makes it so weird, is that it possesses negative pressure.
Negative pressure. It sounds counterintuitive. I mean, when we think of pressure, we think of air pushing out on the inside of a balloon. It's a positive outward force. So why is this negative pressure so crucial, and how does it translate into cosmic repulsion?
It's the essential trick. In Einstein's general theory of relativity, it's not just mass and energy that contribute to gravity. Pressure does too. Positive pressure, which all normal matter has, actually adds to the gravitational attraction.
Okay, so it helps pull things together.
Right. But negative pressure does the opposite. It creates a repulsive gravitational effect. So you can imagine gravity from all the matter trying to pull things together, but dark energy is this uniform background energy that's constantly, relentlessly pushing space apart.
And what's really vital here is how its density behaves over time, right? Dark matter density dilutes as the universe expands.
Of course. The same amount of dark matter gets spread over a larger and larger volume, so its density drops.
But dark energy is different. It's vacuum energy. It's intrinsic to space itself.
Precisely. So if you create more space through expansion, you automatically create more dark energy to go with it. As the universe expands, the density of dark energy remains essentially constant.
While the densities of ordinary and dark matter keep decreasing.
Exactly. And that means dark energy's repulsive force steadily increases its dominance over time. Billions of years ago, matter's gravity was winning and the expansion was slowing down. But eventually, dark energy's constant push took over, and that's when the expansion started to accelerate.
This overwhelming dominance and its repulsive nature, it really confirms that dark energy is the primary driver in determining the universe's ultimate destiny. Whether we coast into a cold, dark future or violently rip apart, it depends entirely on how static or how dynamic that 70% really is.
And if the universe is accelerating, it means dark energy has won the long-term struggle against gravitational attraction. But if this model is so foundational and the evidence for accelerated expansion is so strong, why are we now seeing these signs that the model might be flawed?
Because measuring the rate of that acceleration is proving to be an absolute nightmare for cosmologists. And the conflict has really reached a tipping point.
The Hubble tension.
The Hubble tension.
Yeah.
Okay, let's dive into this because this is the core conflict. You're talking about the most fundamental number in all of cosmology. Hubble constant, written as h0, h $. This number represents the current speed or rate at which the universe is expanding.
H dollars is the cosmic odometer. I mean, if you know H dollars precisely, you have a very good estimate of the age of the universe and you can predict its future trajectory. So you'd expect, given all our sophisticated instruments and decades of refinement, that we would have converged on a single precise value by now.
But we haven't.
Not even close. Instead, we have a significant, persistent, and frankly growing discrepancy between two different methods of measuring it.
Let's ground the units for a second because they're a little strange. The Hubble constant is measured in kilometers per second per megaparsec. So, what exactly is a megaparsec and why do we use these units?
That's a great question because it really helps visualize the scale we're talking about. A parsec is a unit of distance, about 3.26 light years. A megaparsec, or MPO, is a million of those.
So about 3.26 million light years.
Right. So when we say the expansion rate is, for example, $70 in Kikawan, what we mean is that for every megaparsec of distance separating two objects, that distance is increasing by 70 kilometers every single second.
Not because the objects are moving through space, but because space itself is expanding between them.
That's the key distinction. So the farther away a galaxy is from us, the more space there is between us, and the faster it appears to be receding.
And the Hubble tension arises because two entirely separate, really sophisticated methods used to determine this each dollar value. They just give results that clash significantly.
The sources really categorize this conflict by cosmic era. You have measurements that are based on the early universe versus direct measurements from the late universe, which is basically the present day.
Okay, let's start with the early universe perspective, the CMB measurements. This involves studying the cosmic microwave background. The CMB, as you said before, it's the light that was emitted when the universe cooled down enough for atoms to form. That was about 380,000 years after the Big Bang.
It gives us this incredibly detailed snapshot of the universe in its infancy. We can see tiny temperature fluctuations in that light, which were the seeds of all future structure.
But how do you use a picture of the baby universe to calculate today's expansion rate?
You have to feed that data into the predictive framework of the Lambda CDM model. You tell the model, here's what the universe was made of back then. This much matter, this much dark matter, this much dark energy. And then the model projects forward 13.8 billion years to predict what the expansion rate should be today.
And this projection consistently spits out the lower value for the Hubble constant.
Consistently. Using data primarily from the European Space Agency's Planck satellite, the established early universe benchmark is around $67 for PM 0.5 text tone, and that number is very strongly tied to the stability of the Lambda CDM model. If that number is right, the model is in good shape.
Okay, so 67.4. Now let's compare that to the other method, the late universe, or direct measurements.
These measurements use what's known as the cosmic distance ladder. It's a method of building up distances piece by piece, starting with things that are close to us.
And this method relies on finding a series of astronomical objects whose intrinsic brightness we can somehow calculate. We call them standard candles.
Exactly. If you know how bright something truly is, you can figure out how far away it is just by measuring how dim it appears to us. The distance ladder starts with nearby objects, like a special type of star called a Cepheid variable.
Cepheid variables are great because they pulsate, and their pulsation rate is directly linked to their absolute brightness. So you can measure the pulse, know the brightness, and calculate the distance.
Right. We use them to calibrate the distances to nearby galaxies. Then we use those calibrated distances to measure a much brighter, more distant type of standard candle, type Ia supernovae.
These are the exploding stars that led to the discovery of dark energy in the first place.
The very same. Type Ia supernovae are catastrophic explosions of white dwarf stars that happen when they reach a very precise mass limit called the Chandrasekhar limit. Because this mass limit is always the same, the resulting explosion always has the same intrinsic peak luminosity,
which makes them superb, highly reliable standard candles for measuring the distances to very, very distant galaxies.
And these direct measurements, which have been refined with powerful new data from instruments like the James Webb Space Telescope, they consistently show a higher value for the Hubble constant. These recent measurements are all clustering around 74 text kilometers, 72. So, wait, the early universe prediction is 67, and the direct measurement today is 73. That's a gap of 6 or 7 units.
And that gap is statistically significant. The error bars on these measurements do not overlap. This isn't just a small disagreement anymore. It's a genuine contradiction.
So what does that mean? It has to be one of two things, right?
Right, either one set of measurements is systematically flawed, maybe there's some unaccounted for dust effect, or some subtle miscalibration in the distance ladder that we haven't found yet.
Or the model itself is wrong. The Lambda CDM model that we use to bridge the gap between the early and late universe is incomplete. And that's the implication that keeps cosmologists up at night. The need for new physics. If the universe expanded differently in the past than Lambda CDM predicts it should have, it suggests we're missing a critical ingredient.
Maybe an interaction that subtly increased the expansion rate at some point between the time the CMB was formed and today.
This is exactly where the tension becomes so crucial to our ultimate destiny. If New physics is required to fix the current expansion rate. That new physics very often involves modifying the behavior of dark energy.
So the cosmological constant lambda might not actually be constant.
It might not be. It might have been more potent in the early universe, or it may behave differently in the far future. If the nature of that 70% component is dynamic rather than static, that completely changes the trajectory of the universe.
So the Hubble tension isn't just an academic problem. It's the first real sign from the data that the big freeze might not be our guaranteed fate.
Exactly. The predicted rate of expansion is our primary lever for predicting the future. If we can't even agree on the current rate, then our predictions for the next trillion years are shaky at best.
Yeah.
This forces us to move from the one preferred prediction of lambda CDM to exploring the full, wild range of cosmic possibilities.
Okay, so we've established the basics. The universe's geometry is flat, the expansion is accelerating, and the ultimate fate depends almost entirely on the behavior of dark energy. If dark energy is static, we get one outcome. If it's dynamic, we open the door to far more dramatic possibilities.
And the central parameter that defines the future is something called the equation of state parameter, written as a lowercase dollar. This parameter relates the pressure of a substance to its energy density. For our purposes, dollars is the master switch. Its value determines how dark energy evolves and whether the universe coasts, collapses, or just rips itself apart.
Let's start with the first scenario then, the one predicted by the current standard model. Scenario 1, the big freeze or the heat death. This is the most likely path.
This is the outcome predicted by standard lambda CDM. The big freeze is what you get if dark energy behaves precisely as a static cosmological constant, as lambda.
And the condition for that is what in terms of dollars?
The condition is straightforward. The equation of state parameter, $2, must be precisely equal to -1. Dollars equals -911. If that's the case, the density of dark energy remains constant even as space expands. This ensures eternal expansion, but crucially, the acceleration rate will eventually plateau and settle down. It won't run away.
So the process isn't sudden. It's the ultimate slow burn, or I guess the ultimate slow freeze.
That's a better way to put it. The universe continues to expand infinitely, but it just becomes colder, darker, and profoundly empty. The end isn't sudden violence, it's a state of maximum entropy.
Entropy being a measure of disorder, essentially.
Right, a state where all available energy has been evenly distributed throughout the universe. And when that happens, nothing interesting can ever happen again. No work can be done. It's the heat death of the universe.
To really appreciate the time scale here, you have to just throw out every reference point you have for time.
Completely. The current age of the universe is about 13.8 billion years. The stellar era, the period of time when new stars are actively being formed from gas clouds, that only lasts until about 10-14 years. 100 trillion years.
100 trillion. That's more than 1,000 times longer than the universe has even existed so far. How can we possibly model physics on that kind of timescale?
We have to rely on the established laws of thermodynamics and nuclear physics, and we make a big assumption that those fundamental laws don't change over time. We know that the fuel for stars is finite. Over that 100 trillion year period, the great reservoirs of star-forming gas will be completely exhausted.
And the last stars, the red dwarfs, which are the smallest and longest lived, they will finally sputter out.
That's right. Once star formation ceases, the visible universe goes dark. The only objects left will just be cold, dark, stellar remnants. White dwarfs, which will eventually cool and crystallize into what we call black dwarfs, neutron stars, and of course, black holes.
And all these remnants will just drift apart from each other, separated by these exponentially increasing stretches of cold, empty space.
But even these structures are not permanent, and this is where things get really hypothetical. There's a question about the stability of matter itself. Some theories, which stem from what we call grand unified theories, or GUTs, predict that protons are not eternally stable.
Proton decay. So the fundamental building blocks of all atomic nuclei might eventually fall apart.
If this mechanism is true, and we have no experimental evidence for it yet, then over a staggering time scale of perhaps 10 to 10 or 4 years, the protons themselves will decay into lighter subatomic particles. And that would eliminate the last vestiges of ordinary matter structure.
So even the dead stars would just dissolve into radiation.
But even if protons don't decay, there's another mechanism for the ultimate cosmic cleanup. Black hole evaporation, which is driven by Hawking radiation.
Ah, yes. Stephen Hawking's big discovery, the idea that black holes aren't truly black.
Exactly. Quantum fluctuations near the event horizon, the point of no return, cause pairs of virtual particles to pop into existence out of the vacuum. Normally, they just annihilate each other immediately.
But near a black hole, one can fall in and the other can escape.
Precisely. The one that escapes carries energy away with it, and that energy has to come from the black hole's mass. So incredibly slowly, the black hole radiates its mass away and evaporates.
How long does something like that take? If the universe is 100 trillion years old when the last stars die, how much further into the future are we talking for black holes to disappear?
The timescales are literally unimaginable. A black hole with the mass of our sun would take approximately $10 years to completely evaporate. A 1 followed by 67 zeros.
And the supermassive ones at the center of galaxies.
A supermassive black hole could take up to 10 years. That's a number so large it's called a googol.
A 1 followed by 100 zeros.
Yeah.
It's just a meaningless number.
It is. But once every last black hole has evaporated, the universe will be nothing but a cold, ultra-sparse soup of fundamental particles, electrons, neutrinos, and incredibly low-energy photons, all stretched by expansion to carry almost no energy at all.
The temperature approaches absolute zero. The expansion continues indefinitely, just gently coasting into the final, silent big freeze.
That is the fate we currently default to, the standard prediction.
Okay, now let's consider the alternative. The scenario that would result if the new physics needed to solve the Hubble tension involves making dark energy just a little bit more aggressive. This is scenario 2, the Big Rip.
The Big Rip hinges entirely on dark energy being dynamic. Not a constant vacuum energy, but a scalar field, which is sometimes called quintessence, that can fundamentally change over time. More specifically, this scenario requires the equation of state parameter, tollers, to cross a critical threshold. It has to become numbered under 1,1.
So it has to drop below -1. And when that happens, we enter the realm of phantom energy.
Phantom energy. It's a highly unstable mathematical prediction because it implies that the energy density of dark energy does not remain constant, nor does it dilute. It actually increases as space expands.
Wait, hold on. If the volume of space is increasing, but the energy density is also increasing, that implies total energy is just being created out of nothing, right?
Okay.
Doesn't that violate the law of conservation of energy?
That's a crucial challenge and a great question. It does violate something called the null energy condition, which is a fundamental tenet of general relativity. It basically states that energy density should never be negative for any observer.
So how seriously is phantom energy actually taken in cosmology?
It's taken seriously as a theoretical possibility that comes out of the mathematics of general relativity. And models that involve it are interesting because they can be used to describe an extremely quick, explosive acceleration, which might just be what's needed to resolve the Hubble tension. It's a potential, if extreme, solution.
And if that phantom energy exists, it creates a runaway feedback loop.
A terrifying one. Faster expansion leads to a higher density of dark energy, which in turn leads to even faster expansion. It creates this ever-escalating repulsive force that eventually becomes so powerful it overwhelms all of the fundamental forces of nature.
And the Big Rip doesn't happen all at once, does it? It's a sequential destruction.
Terrifyingly sequential, yes. It's defined by the strength of the bonds being overcome. First, the expansion tears apart the weakest structures.
So galactic clusters. They're bound by the relatively weak force of gravity over vast distances. They get ripped apart first. Their member galaxies just fly away from each other so fast that they disappear beyond each other's observable horizons.
Next, the destruction moves inside the galaxies themselves. The internal gravitational bonds holding stars in orbit around the galactic center are overcome. Galaxies are unbound.
Stars are just flung into the void.
Planetary systems would follow. The Earth would be stripped from the sun's gravitational influence and just thrown out into the expanding darkness.
And the final, critical stage of the Big Rip is the destruction of matter itself. The repulsive force of space becomes stronger than the electromagnetic forces holding molecules together, then stronger than the forces holding atoms together.
And in the last fraction of a second, the overwhelming spatial expansion tears apart the strong nuclear force, ripping atomic nuclei apart into their constituent quarks and gluons. Space-time itself reaches a singularity, not as a collapse, but as an infinite expansion of density and scale factor, utterly annihilating matter down to its most fundamental level.
And the sources all emphasize that while the Big Freeze timescale is vast, the Big Rip happens suddenly once the acceleration hits that critical velocity. It's an immediate, violent end that only requires a very subtle shift in the nature of that mysterious 70% of the universe. just moving dollars from exactly -1 to something slightly below it.
A tiny mathematical change with the most catastrophic physical consequences imaginable.
All right, let's cover the next scenario, which used to be the front runner before we discovered dark energy. Scenario 3, the Big Crunch.
Yes, the oldest, most classical cosmic ending. Before the discovery of accelerated expansion in the 90s, this was a highly plausible scenario, and it was often tied to these ideas of cyclical universes.
So what's the condition required for a Big Crunch?
The required condition is that the universe's total matter density, both the baryonic and the dark matter, has to be significantly high. High enough that its collective gravitational pull can eventually overcome the initial outward momentum of the Big Bang and any repulsive influence.
So gravity has to win in the end.
Gravity has to win. If that condition were met, the expansion would slow down, stop, and then reverse, initiating a catastrophic contraction. It would be the ultimate reversal of the Big Bang.
What would that reversal actually look like from, say, our perspective?
The cosmic background radiation, which is currently cold, around 2.7 Kelvin, would begin to blue shift dramatically. Its wavelength would shorten and its energy would increase, so the entire sky would start to heat up.
And the galaxies would stop receding and start rushing toward one another.
Temperatures would soar, space itself would compress until everything collapses back into an infinitely dense, hot final singularity. A reverse Big Bang. This model really appealed to theorists for a long time because it so elegantly provided an answer to the question, what came before the Big Bang?
It suggests the crunch just feeds a new bang.
A cyclical process. But the sources we've reviewed are absolutely definitive on the verdict here. The discovery of accelerated expansion driven by dark energy means that the Big Crunch scenario is highly unlikely.
Our universe just doesn't seem to have enough matter to make it happen.
Not even close. Dark energy currently dominates the universe with its 70% share, and its repulsive force is far too strong for gravity to ever successfully reverse the process, unless dark energy itself were to somehow dissipate or change its nature entirely in the far future, which is pure speculation.
Okay, so with the Big Crunch mostly ruled out, that brings us to its modern cousin, Scenario 4, the Big Bounce. This is a way to preserve the idea of an oscillating cyclical universe, but with a quantum twist.
Right. The Big Bounce still requires an initial contraction phase, just like the Big Crunch, but it introduces physics at the absolute extreme limit of gravitational collapse to prevent the singularity from ever forming.
So it's an alternative ending for a high-density, closed universe that wants to avoid the problem of infinity.
Exactly. So if the universe were to contract, what physical mechanism could possibly stop it from collapsing into an infinitely dense point? This is where models based on theories like loop quantum gravity or LQG come into play.
LQG is one of the attempts to unify quantum mechanics with general relativity, right?
It is. And within these models, space-time itself isn't infinitely divisible. It's quantized. It's made of discrete minimal units like pixels on a screen. This minimum possible size creates a massive, inherent repulsive force at extremely high densities.
Like a quantum spring that pushes back when you compress it too much.
That's a great analogy. That quantum repulsive force acts as a hard limit. As the contracting universe approaches the Planck density, the maximum theoretical density possible, this quantum force halts the collapse and causes the universe to bounce back outward.
And that bounce initiates a new, hot expanding phase. A new Big Bang.
In this view, our current universe is just one phase in an eternal sequence of collapses and expansions, always dodging the singularity at the last moment through quantum mechanics.
It's a really compelling philosophical concept, suggesting infinity in time rather than space. But again, the current cosmological data are flat geometry and the dominance of dark energy. They don't naturally lead to the contraction that's necessary for a bounce to even begin.
Not without some new, currently unknown reversal mechanism in the distant future. It remains a fascinating but observationally unsupported idea.
Finally, that brings us to the most traumatic, instantaneous, and maybe the least predictable end of them all. Scenario 5, the Big Slurp.
Yes, the Big Slurp. This isn't governed by density or expansion rate. It's a sudden quantum catastrophe that could, in theory, happen at any moment, right now.
Which is a comforting thought.
It is. This concept stems from the idea that the universe we inhabit, with our specific physical laws, our particle masses, our forces, is currently residing in what's called a metastable state, a false vacuum.
Okay, let's use an analogy to clarify this idea of vacuum states.
Imagine a ball resting in a shallow valley on a hillside. This shallow valley represents our current false vacuum. It's stable for now, the ball isn't rolling, but if that ball gets even a slight nudge, It could roll over a small hill and then fall into a much deeper, much lower energy valley at the bottom of the hill. That's the true vacuum.
So our universe is the ball sitting in that shallow, false vacuum. It's stable, but it's not absolutely stable.
Exactly. And the physical constants that govern our reality, the mass of the electron, the strength of the nuclear forces, the characteristics of the Higgs field that gives particles mass, they are all defined by the energy level of our current vacuum.
So what happens if we fall into that lower valley, the true vacuum?
The Big Slurp theory suggests that the universe is constantly attempting to tunnel through that energy barrier into the true vacuum state. It's a purely quantum mechanical process, so it's random and completely unpredictable.
At any moment, somewhere in the universe, a tiny region of space could just quantum mechanically transition.
It's like supercooled water that's below freezing but still liquid. If you disturb it, it instantly crystallizes. Once this transition starts somewhere, a bubble of the true vacuum begins to expand outward at nearly the speed of light.
And inside this bubble, the laws of physics have been fundamentally rewritten.
The ground state of the universe is now lower, but the rules are all different. The constants have changed.
So what happens when that bubble hits us?
Instantaneous and total destruction of all known structure. The changes in the fundamental constants, the mass of the Higgs boson could change, the strong force could become weaker. It would make it impossible for atoms or even atomic nuclei to hold together under these new rules.
So life, molecules, matter as we know it.
Yeah.
It would just be instantly unmade as this bubble washes over us.
There would be no warning. Unlike the Big Freeze or the Big Rip, which require trillions or billions of years to unfold, the slurp is an instantaneous rewriting of reality.
But there's a cosmic limitation here, isn't there?
Yes, and it's an interesting one. Because this bubble of decay spreads outward at the speed of light, and because the universe is currently accelerating its expansion, the parts of the universe that are already receding from us faster than the speed of light would never be reached by the bubble. It could never catch them.
So from a grand cosmic perspective, the universe might actually survive the slip, just not our local patch of it.
Chilling thought.
So we have 5 destinies. 3 of them, the crunch, the bounce, and the slurp, are pretty unlikely based on our current data, which means the real choice is between the remaining 2. The Big Freeze, which is slow and cold and requires Eliza level 1, and the Big Rip, which is fast and violent and requires NISA level 1.
And that choice hinges entirely on the dynamic nature of the 70% of the universe we don't understand, which takes us right back to the Hubble tension. That crisis is forcing us to confront whether D'Ehlers is truly fixed to -1 or if it needs to be just slightly below it to explain the expansion discrepancy we see today.
This has been an incredible tour through the mechanisms of cosmic endings. Let's try to synthesize the key threads we've pulled together for everyone listening.
I think the first and most important takeaway is that the sheer scale of the invisible universe dictates everything. You simply cannot predict the end of time without acknowledging that 95% of cosmic density is dark matter and dark energy. We are truly flying blind in the long term.
Second, the current, most successful framework we have, the Lambda CDM model, dictates the most anticlimactic, yet most certain-seeming end, the Big Freeze. A slow death driven by maximum entropy over vast eons, all based on the crucial assumption that dark energy is a static cosmological constant, where Dali equals exactly -1.
Third, the final destiny depends entirely on that exact dynamic behavior of dark energy, which is codified in that equation of state parameter, $2. A tiny, tiny movement of $2 to be to just below -1 fundamentally changes the outcome from a gentle fade into a violent universe-ending catastrophe, the Big Rip.
And fourth, and this is the key, the Hubble tension, that persistent measurement gap between the early universe CMB data predicting 67 and the late universe distance ladder measuring 73, that's the signal that Lambda CDM might be incomplete. It's a crisis that demands new physics, which in turn implies that the properties of dark energy may be dynamic, opening the door for the Big Rip to be a serious contender.
It really is humbling to reflect on those immense timescales. 1014 until the last star dies. A Google years for the last black hole to evaporate. The Big Freeze is an incomprehensible cold silence. A slow dispersal that reduces all of reality to fundamental particles just coasting into eternity.
And compared to that long, drawn-out fade, the Big Rip offers such a stunning alternative. It's a violence so extreme it destroys the very bonds that hold atoms together. It's a definitive, swift, and total unmaking of reality, driven by the escalating tyranny of phantom energy. And the difference between those two destinies is mathematically tiny, yet physically absolute.
Indeed. We are currently living in a golden era of cosmic transition, a time where dark energy is firmly establishing its dominance over matter, accelerating us all toward this unknown future. The most exciting physics right now is focused on resolving that Nasi$1 boundary. Is it a wall or is it a line we can cross?
So what does this all mean for you listening to this? If the only way to resolve the Hubble tension and unify the early and late universe measurements is to introduce some form of new physics that makes dark energy slightly dynamic, what fundamental property of dark energy is the most likely to change?
And is it possible that the required modification to lambda CDM is one that pushes the value of $2 just enough below -1 during the universe's past to accelerate the expansion to the rate we measure today? And if so, does that very same mechanism also condemn us to a big rip in the far future? The scientific community is currently sifting through that 70% of the universe we still barely understand, seeking the true dynamic nature of dark energy, which holds the key to our ultimate cosmic destiny.